Now, I'd like to see that we actually make the rotation by the angle alpha. For that, I will compute the dot product between the x and the t of x, because in order to find the angle between the x and the image of x, or the cos of that angle, I need to do that via dot product. That's the very robust way to do that. I'm sure you know that from your elementary studies of vectors. So here's my dot product between x and t of x. So what I do, I just take the components of x, here they are. I take the components of t of x, here they are. Here's my dot product. Fully expanded. Fully expanded. Now if I do the expansions in these brackets and these brackets, here's the expansion. x1 squared cos alpha, it's this expansion. This term of the expansion, negative x1, x2 sine alpha, it's from here. Now, if I expand the brackets here, it will be x2, x1 sine alpha and x2 squared cos alpha. Here's the expansions. Again, we see that these mixed products, they will cancel each other. And the remaining two, they give me x1 squared plus x2 squared times cos alpha, which again can be shortened to the modulus of x squared times cos alpha. So if I say that the theta is angle between x and t of x vectors, then we know how to compute such an angle. The cos of such an angle theta will be the dot product of x and t of x divided by the length of these individual vectors. And every component here is pre-computed already, isn't it? Dot product is here. The length of t of x is here. If you sub in everything in and do some cancelling, you will see that the cos theta is cos alpha. So my original cos alpha, which was set in my transformation, which from the beginning we didn't know it's a rotation. Effectively, the angle between the image and x itself, it is the same as the angle alpha in the base of my transformation. Any questions? Well, if you don't have any questions, I have a question for you. Is it enough to conclude that my t built like so? I mean, is it enough evidence I presented here that t built like so is a rotation by the angle alpha counterclockwise? Is it enough? Yes or no? I think you're right, actually. I mean, what you're saying, actually, if you have a vector x and you have another vector of which you know, if you have one vector and if you have another vector of which you know that this new vector of the same length and the angle between the two is alpha, it doesn't uniquely define the vector yet. It may be one to the left or maybe to the right. Is that what you're saying? Right, so we need some more evidence to show that this is exactly counterclockwise, not clockwise, for instance. Where do we search for such evidence? What other tool from the vector calculus, elementary vector calculus, will help to deliver such an evidence? Cross product, or actually I suggest triple scalar product. It's something which will help you to see which way we're going, left or right. Well, the problem is here on the plane, we don't have any triple vector product on the plane. So what we should do is what I call the embedding of two-dimensional plane into three-dimensional space. Here it is. Thank you. It's actually a very good suggestion. First, I suggest to consider the mapping, which I will call I, from two-dimensional vectors into three-dimensional vectors. And that is the mapping which is defined like this. If I take a vector x1, x2, the result will be the vector with three components, where the third component is simply 0. I claim, well, actually, that such a map is called the embedding of R2 into R3. It will be a linear map. It's a side comment, actually. It's irrelevant for the present presentation, but it will be an example of a linear map. It's another very important example, which shows you how two-dimensional space can be embedded into three-dimensional space. It's not the only way. There may be some other ways, but it's one of the canonical ways. And then I will compute, look what I'm going to do. If I call the A is the image of my x vector from here, from these considerations, in a three-dimensional space, And if I call B is the image of my T of x in three-dimensional space, I'm going to compute this triple scalar product between the vector A, it's my image of my x in the three-dimensional, my B, and my third standard basis vector. So basically you have your plane where you have a vector and the image. Before we just lived in that plane, but now we'll lift it ourselves out of that plane with the help of this embedding. Now we live in a three-dimensional, so we throw extra vector E3, and we compute this triple scalar product, and that will give me the direction of the rotation. Because this is supposed to form right-handed triple, something you'll learn when you discuss these triple scalar products and cross products. I have only 1 minute for that. Let's just do that. Let's just finish this computation. I'll lift it up. Let's just finish these computations. We all know how to compute the triple scalar products. We take the components of the third vector, E3. We put it in the first row of my determinant. Second row will be the components of my vector A, and that's the components of my B vector. Here it is. Here's my embedding. You see my x vector embedded into three-dimensional space. That's my 0-third component. Here's my T of x vector embedded into three-dimensional space. 0-third component, and here's my E3 vector. It's a very simple determinant. If you use the decomposition by the first row, it will be this one times this minor. Here's the minor. And all we need to do, we need to compute this 2 by 2 determinant. Let's just do that. We all know how to compute the determinant. It's this x1 times this entry. And take this x2 times this entry. If you do the expansion, here's the expansion, x1 square sine alpha, mixed product x1, x2 cos alpha, take x2, x1 cos alpha, and plus x2 square sine alpha. Mixed product cancels out. Squares are combined with a common factor sine alpha, and the result is length of modulus of x times sine alpha. So if you look at the alpha angle, which is less than 180 degrees, which will make this product positive, which will make this triple of vectors forming right-handed triple. And the right-handed triple in particular implies that the turn from A to B, seen from the tip of the vector E3, counterclockwise. And when alpha is larger than 180 degrees, sine is negative, and this turn will be seen as clockwise. So this is exactly the counterclockwise rotation by the angle alpha.